all, we talk about like the basic shape of the quadratic equation. So the simplest parabola graph will have the rule of y equals to x squared. Okay, that's the easiest one. Y equals to x squared. And I believe year 9 you have learned this. What we have done is we set up a table with x values and y values, and we give a couple of points to see what the trend of graph will be. So let's say we put -3, -2, -1, 0, 1, 2, and 3. And we can have 9, 4, 1, 0, 1, 4, 9. We can find those points, okay, because it's y equals to x squared. When I have those value of x, I can square the x value and we can find the y value as well. Okay, we can find the y value as well. So we have coordinates -3, 9, -2, 4, and like ... 3, 9. In the middle we have 0, 0, and so on. So when we plot those points on the Cartesian plane, okay, when we plot those points on the Cartesian plane, so -1, 2, 3. So 3, 9 is this point here. -2, 4 is this point here, and -1, 1 is this point here, 0, 0 is this point, 1, 1 is this, 2, 4 is that, 3, 9 is this one. So after assume we don't have this graph before, and now we plot those points on the graph and we can connect it by a smooth line. So we kind of have this like this parabola shape. Okay, have this parabola shape. So that's my easiest graph. Okay, easiest rule for quadratic equation. So when we're trying to observe this graph, what we can see is we have a turning point. Okay, turning point is the key feature for a quadratic relation. Okay, you know when you sketch for linear, I need to label x-intercept, I need to label y-intercept. So for quadratic, we still need to label x-intercept, we still need to label y-intercept, but plus we also need to label the turning point. Like, what do I mean by label? You put the coordinates near the turning point. So that point is 0, 0. So I need to label the turning point. Also, we look at this graph, we have a minimum value, which is the turning point. So therefore, we call this turning point as a minimum vertex. Okay, so turning point is also with name of vertex. So this is the minimum value of the vertex. Okay. And this graph is a symmetrical graph. If I draw a line vertically like this, you can see the left-hand side and right-hand side, they are symmetrical. So it is symmetrical graph, symmetrical about the line x equals to 0. Okay, it's symmetrical about the line x equals 0. So you can see it's symmetrical by that vertical line. And also we can see xy intercept is just 0, 0. Okay, it's just 0, 0. Okay. Now we'll introduce some, well, you know the graph is not going to be exactly looks like that. You will have 3 ways to do transformations. Okay, there are 3 ways we can change the graph. Like we have a graph looks like this. I can do different things to that. I can stretch it, I can reflect it, or I can move it. Okay, move it to different place. So how all of this transformation can be viewed from the equation. Okay, when I see this equation, how I can know what happened to the y equals to x squared graph. So there are 3 things we can do. We can stretch it, which is the dilation. I can stretch it this way, make it fatter or make it thinner. Or we can reflect it, like it's originally this way. I can reflect it to make this way. So I call this is a happy face and this is a sad face. Okay, this is happy, this is sad, so reflect it. Or I can translate it. Can translate up or down. Okay, translate this way. Or I can translate left or right. So I can do the translation as well. Okay, so what we can see from that. So first of all, we see the dilation. You can see my one with different colors. The green one is y equals to 2x squared. The red one is the original one, that's y equals to x squared. And the blue one is y equals to a half x squared, okay, a half x squared. My question is, do you think the higher, like we have y equals to ax squared, okay, this is a coefficient of a, y equals to ax squared. The larger the a value, the thinner the graph or the fatter the graph, the wider or the thinner. The larger a, if I have a higher a value, so a is 3, a equals to 4, do you think the graph will become thinner and thinner or wider and wider? Thinner, okay? So you can see a half is most outside, 1 is like middle, and then 2 is like even inside, it's like thinner. So if I have this one, something like that, that can be y equals to 3x squared. So the larger the a value, the thinner the graph. So it's not going to change anything else. Like it's still facing like this way, still have turning point at 0, 0, but all we have done is make the graph become thinner. So if I sketch another one outside, this one will be y equals to maybe a third x squared, okay, a third x squared, like smaller than half, a third x squared. So a is, okay, so there's different values. So what a is doing, a is changing the change the graph to wider or thinner. That's what's the a doing. Okay, now we can see the next one. The red one again is the most basic graph. Now my a value become negative. Okay, become negative. Well, it's still negative 1 and negative 2. Okay, negative 1 and negative 2. So what's this negative doing? Like it's still changing the a value. Still a like is different from 1. So I want to make a negative 1 is a reflection. Okay, the negative of a is reflecting the graph. Okay, it's making it reflect in the x-axis. So it's having a minimum before and now after reflection I have a maximum turning point. So it's doing the reflection when the a is negative. Okay, so when a is negative. So reflection in x-axis. Okay, and we can see the blue graph and the green graph. The blue one is thinner, right? The blue one is thinner. Like this one is thinner, negative 2x. But remember you said a is larger. Graph is thinner. Okay, the larger the a, the thinner the graph. That's the conclusion we make from the first one. But if you think about the second one, negative 2 and negative 1, which one is larger? Negative 1 is larger, right? According to what we have, a is larger, the graph should be thinner. Okay, the graph should be thinner, but you can see the negative doesn't really follow that. So when we consider like whether thinner or wider, we don't take the negative sign into consideration. So we do not think about negative 1 and negative 2. We just think about 1 and 2. The negative is only doing reflection. Okay, it's only in charge of reflection. It's not going to change how wide the graph is. It's only the actual value of 1 and 2 that changing the wideness, but not the negative. So when we think about the graph is wider or thinner, we don't take the negative into consideration. So now if we just consider 1 and 2, 2 is larger than 1. Therefore, the negative 2 will get a thinner graph. Okay, we'll get a thinner graph. So the negative only doing the reflection. It's not going to change the wideness of the graph. Okay, last one is a translation. This is the most complex one. So translation, there are two translations. There's a vertical translation and a horizontal translation. Okay, there's a vertical translation and a horizontal translation. Let's think about the vertical translation first. Okay, vertical translation first. The red one again is still the most original graph. And then the blue one, the dark blue, the navy one is x squared plus 2. And the purple one is x squared minus 3. You can see the turning point. The turning point is moving, right? This turning point is 0, 0. This turning point is 0, 2. This turning point is 0, negative 3. The most obvious translation can be viewed from the turning point. Where is your turning point? That will tell you what is your translation. So originally it's at 0, 0. I have plus 2 at the back of the function. So the graph has been shifted by 2 units up. So the turning point will be shifted by 2 units up as well. So 0, 0 becomes 0, 2. The bottom one is x squared minus 3. So it has been shifted down by 3 units. So the most obvious point will be the turning point as well. 0, 0 moved down by 3 units. That gives you 0 and negative 3. So the vertical translation is very easy to see. It is the value add after the x squared. Okay, you add after the square. So you add at the back of the square. So if k is positive, it's moving up. If k is negative, it's moving down. Okay, so you adding means you moving up. You subtracting means you move down. But let's have a look at the horizontal 3 graph. The red one is x squared, it's the original one. The light blue got an x plus 3 squared. Okay, we haven't plus anything at the back of square. We combine it with the square. So it's x plus 3 squared. And this green one is x minus 2 squared. Okay, so you can see this is a horizontal changing. When we combine the number with the square, it's a horizontal movement. Okay, it's a horizontal movement. So we have x minus h squared, or x plus h squared. So we have x squared minus k and x squared plus k is moving down and moving up. We have x minus h squared and x plus h squared. You can see plus the h means move to the left and minus the h means move to the right. You can see from my graph, the light blue is a plus. Compared to your original red graph, it has been shifted to the left. And also we got the turning point of negative 3, 0. So it's moving by 3 units to the left. X minus 2 squared is shifting to the right by 2 units. So this turning point is 2, 0. So minus 2 means move right by 2 units. And plus 3 means move to the left by 3 units. Okay, so if you subtract means you move to the right. If you plus within the square, which means you move to the left. But if you're adding after the square, is moving up. You're subtracting after the square is moving down. So what we have is this is a downward movement and this is an upward movement. Okay. Now let's have a look at one question. If I have y equals to minus a half x plus 1 squared minus 2. Can you tell me what has been done to this graph compared to y equals to x squared, please? Okay, is there any stretch, any reflection, any movement, horizontal, vertical? The turning point will become what? Can you tell me anything you know? Anything you can see? Sorry? Yeah? Yes,
okay, so it's reflected in the x-axis.
Reflect in x-axis? Okay.
And then
try another one. Yeah, Ali. Yeah. Move down by 2 units. Okay, yes, correct. Anyone else? Kamini?
Wider by half.
Wider? Nasha? Move to the left by 1 unit. That's correct. What's the new turning point? Okay, new turning point is -1 and -2. Correct. Okay, so that's all. Everything has been done compared to y equals x squared graph. So if you have y equals x squared graph, looks like this. Now the graph is wider and has been reflected, has been moved to the left and also moved down. So that is what has been done to this graph. Okay, we all get that. That's good. All right. Let's have a think about the example here. Well, it's a very easy example. If you have y equals to 4x squared, I should have a minimum turning point. Okay, the maximum minimum means asking you, is this graph having a minimum value or a maximum value? So you know the graph still looks like this way, so I should have a minimum value. Reflect in the x-axis, yes or no? Well, we don't have reflection, like there's no reflection, there's no negative, so I don't need to reflect the graph. The turning point is still 0, 0 because there's no horizontal or vertical movement, so it's still 0, 0. The y value when x equals to 1, so I sub x equals to 1 in, I should have y equals to 4. Okay, sub 1 into the function, I have x equals to y equals to 4. Wider or narrower compared to y equals x squared? Well, it's a larger a value, I should have a narrower graph. Okay, that's how you complete this table. So I'll give you 1 minute to complete B and C by yourself, please. And when you finish, you can have a look at my answer. Is that the same as what you have? Okay. Any questions? Yes? Y value? So y to the I sub x equals to 1, so it's -1 squared. It's not -1 bracket squared. Only 1 squared, so it's still 1. And then it's -1 plus 3. No, if I want -1 squared, I should have x minus x bracket squared, then that's 1. That's 1. So if I go minus x bracket squared, that's -1 bracket squared, and that is 1.
So if there's no brackets,
Yeah.
just -1.
think about the calculation rule. Which one we calculate first? We calculate the power first, right? So it's only 1 squared. So what I have is minus 1 plus 3. That make sense? Everyone understand that? That's really important, okay? That's really important. Good question. So it's different. Like minus 1 squared and minus 1 squared is different. Okay? One is minus 1 and the other one is just positive 1. Okay. Please copy this one down. Okay, that is exactly what I have write for this formula. Y equals to negative a half x plus 1 squared minus 2. So this is the general form. This is the general form of, and it's not general form. This is called the turning point form. Of quadratic. Okay, this is the turning point form of a quadratic. So we'll start to sketch our quadratic equation by using this form. It is the most useful form to sketch for quadratic. So every time when I'm trying to sketch a quadratic, I want to make it into this form first and then sketch. There are 3 forms. There are 3 forms for quadratic. I'll introduce the first 2 today. This is called the turning point form. And also we have ax squared plus bx plus c. This is called the general form. This is called the general form, like it's the expanding form. Okay, it's just the expanding form. Can you tell me, do you know why it is called the turning point form? Do you know why it's named under turning point form? Yeah, Michelle? Yeah. Yes, that's correct. You can see the turning point directly from the turning point form. Okay? You can see why it's called turning point form. You can tell us your turning point. Easy like that. So the turning point for this one will be h comma k. Okay, so it is the turning point I can see from this formula. Okay, h comma k is x minus h and plus k. So the h is the x value of the turning point and k is the y value of the turning point. So you can see the turning point from the turning point form. That's why it's very, very useful. Okay, it's very, very useful. Okay. I can easily get turning point from turning point form. What can I easily get from a general form? Well, general forms say like give you general information. What you can easily get from a general form? Just have a think. Yes? The Y-intercept, good. I can easily see the Y-intercept from the general form. Because when I sub x equals to 0, I don't need to do any calculation. I can just sub 0, first one 0, second one 0, the last one is just a c value. So I can easily get the Y-intercept from a general form, not other things at all. There's also a third form, like I'm not going to talk about that today. So we learn next exercise, we can see that. But turning point form is very, very important, and today we're trying to sketch it by using this form. Okay, by using this form. Also, you need to know when a greater than 0 is this way. So I said it's the small one, and when a is less than 0 and is a set one. Okay, so it's a small one or a set one. So remember the shape. So if a is positive, upwards, and if a is negative, it's downwards. We can use the same way when x equals to 0 to calculate y-intercept. When y equals to 0, calculate x-intercept. That's all as normal, exactly the same as before. Okay. By the next couple of questions, can you tell me what are the turning points first? What's the turning point for the first one? 0, 0. Good. What's the second one? 3, 0. Good. And C. What's the turning point for C? 0, 2. Good. How about the last one? Turning point. -1, 4. Good. Okay, so we have labeled all the turning points. So the first thing is find turning point. Okay, the first thing is when you sketch for a quadratic. So the first thing is you're trying to know where is the turning point. When you know the turning point, you know 80% of what you want already. Okay, so if we use this one as example, use D as example, I want -1, 4. Okay, -1, 4. So -1 is here, 4 is here. My turning point is here. -1, 4. The next thing I will consider is which way this graph will go. It's like upwards or downwards? Downwards or upwards? Down. Because A is negative. So here is a negative. So this graph should be this way. Okay. If the graph is upwards, okay, if it's upwards, I will have a graph like about approximately this way, right? Do I have x-intercept for this graph? Do I have x-intercept? No, for this, like for upwards, we don't have, right? So we don't need to find x-intercept at all. But because our graph is a downwards, well, do not sketch it like I just roughly sketch it, like downwards is always this way. Can you see x-intercept here? Yes, so therefore we need to calculate x-intercept. Like you don't calculate x-intercept before you know the rough shape, because there might be no x-intercept. Don't waste your time to trying to find x-intercept when there's no x-intercept exists. When we make sure, yes, we definitely have to x-intercept, then we're trying to calculate that. So therefore, what we'll do next is, what's the y-intercept? Okay, so we're trying to work for y-intercept. When x equals to 0, y equals to -0 plus 1 squared plus 4. Y equals to -1 plus 4. Y equals to 3. Y equals to 3. Zero, 3. Also, you should know, like, the graph is always symmetrical. Okay, for quadratic, the graph is always symmetrical. So it's symmetrical about which line? It will be symmetrical about the turning point. Okay, so this line. When we draw a vertical line at the turning point, it will be symmetrical about this line. So when I know I have a point at 0, 3, I definitely know I should have a point at -2, 3 as well. Why? Because this graph is symmetrical. I have a point on the right hand side of the line. I must have the same distance on the left hand side of the line as well. So I calculate the 0, 3. And also I know it's symmetrical about that pink line. Therefore, there must be another point on the left, which is -2, 3. Okay, which is -2, 3. Also, I need to calculate the 2x-intercept. Okay, I need to calculate the 2x-intercept. So I'll make y equals to 0. So 0 equals to -x plus 1 squared plus 4. How we should solve for this? expand first. We can expand first. Any other ways? Expand is definitely one correct way. Any other ways we can do it? I'll expand it first. Okay, I'll expand it first to see what will happen. Well, I'll move it first to the left-hand side. I don't like the negative there, so I can go for that. I don't like the negative. Move it to the left-hand side. Get rid of the negative, and I'll expand that. X squared plus 2x plus 1 minus 4 equals to 0. So x squared plus 2x minus 3 equals to 0. So x plus 3, x minus 1 equals to 0. So if you do the cross multiply, x plus 3 and x minus 1 equals to 0. X plus 3 equals to 0 or x minus 1 equals to 0. X is minus 3 or x is positive 1. So 1, 0 and negative 3, 0 added to x-intercept. Now I can see I have enough points. Okay, I have enough points. I can just connect them. By a proper 1, 2, 3. Scale is not very nice. It's a quite thin graph. It's approximately like this. It's quite ugly graph because the scale is not that nice. But anyway, something like that. Okay, we have that. Well, you can label all the points, that's fine. 1, 0, negative 1, 2, 3, 1, negative 1, 4, negative 2, 3. That's why I'm not labeling at the correct place. 3 is here. Negative 2, 3 is here. That's why I can't sketch it. 0, 1, that will be better. That's much better. Okay, that's a good graph. Okay. I want to introduce another way to solve for this x-intercept rather than expand it. What we have is 0 equals to minus x plus 1 squared and plus 4. Okay, we have this. What I will do is I'll make the square to the other side. So it's x plus 1 squared equals to 4. Can you tell me what squared can be 4? Or negative 2. 2 squared before, negative 2 squared before. So therefore x plus 1 must be 2 or x plus 1 must be negative 2. So something squared equals to 4. So 2 squared can be 4, negative 2 squared can be 4. That's the only two possibility can give me 4. Okay, on the right hand side. So therefore x equals to 1, x equals to negative 3. That's also another way we can solve for this. Okay, we can solve for this. We treat the x plus 1 as one thing. Okay, we treat that as one thing. So something squared equals to 4. What's the something? The something must be 2 or negative 2. Remember, it needs to be 2 values. It needs to be 2 values. Any questions for this one? Like this is the most complex one among these three graphs. You have turning point, you need to find Y-intercept, you need to find X-intercept, and you need to think about the symmetrical property, and also you need to solve for quadratic as well. Okay, if you don't have questions, let's have a look at example 2. I'll do the last example here, and I'll give you time to complete the other three graphs. For example 2 is, I have a graph here. Okay, I have a graph here. So for this graph, I know the turning point is at -1 and 2. And I also know the graph is passing through a point 1, 4. Okay, for this type of question, asking us to find equations, when turning point is given, we need to use the turning point form. Okay, when you see turning point, then you use the turning point form. You definitely use the turning point form. Okay, again, remember the turning point form is y equals to, we have a here, okay, a, y equals to a x minus h squared plus k. The a, okay, don't forget the a. Like a lot of students just have x minus h squared plus k in the end. Like forget about the a completely. So there is a. Why? Because this a is the dilation. See, I have a turning point at 1, 4. I can also have another graph with the same turning point. You still have turning point 1, 4. So how do you distinguish between the two graphs? Is through A. Okay, A is larger, it gets thinner, A is smaller, it gets wider. So A is in charge of the dilations. So I must have the A there. So because turning point is -1, 2. Because turning point is -1, 2. So this equation must be y equals to a x plus 1 squared plus 2. H is -1, so it's x minus -1. So that's x plus 1. So I should have x plus 1 to have the x value of the turning point to be -1. Okay, that's according to the turning point what we should have. Okay, according to the turning point what we should have. And now the next thing is I need to work out the a value. I need to work out the a value. So I need to sub. Well, I already used the turning point to write the turning point form. So the turning point is a useless information now. Like I already used it. So the only thing left is 1, 4. It's another point on this graph. I can't use the turning point again. Okay, remember, turning point is used to write that line. Finished. That piece of information gone. So I need to sub x equals to 1, y equals to 4. I need to sub x equals to 1, y equals to 4. 4 equals to a, 1 plus 1 squared plus 2. Okay, x equals to 1. This a is still here. This a is what we're trying to work out. Okay, this a is what we're trying to work out. So we minus the 2 to that other side. We have 2 equals to 4a. 2 equals to 4a. So 1 plus 1 is 2. 2 squared is 4. 4a equals to 2. Therefore, a equals to half. Therefore, a equals to half. This 2 to that side, make it 2. 1 plus 1 is 2 is 4a. Okay, so therefore a is a half. Yes? And then we need to write our final statement, which is a half x plus 1 squared plus 2 is the equation for this one. So I need to remember, for finding equation question, I always need A. Okay, I always need A. You can't assume A is 1. Okay, there might be dilations, there might be like wider or thinner compared to x squared. So you must work out A value by yourself. Okay, when you finish this one, go back to the previous page and trying to sketch the graph A, B, and C. Those three are really easy ones, but remember, at least label 2 points on your graph. Okay, so for any graph, you need to label at least 2 points. If you have x-intercept, y-intercept, turning point, you must label them. Okay, you must label them. For this one, I have labeled 1, 2, 3, 4, 5 points. Well, this point is not really necessary, but I must label the turning point, I must label the y-intercept, I must label the 2 x-intercepts. So if you have them, you must label them. If you don't have all of that, you at least need to label 2 points. Okay, at least needs to label 2 points.